Alrighty. It's on. Good morning all. My name is Jago de Vreede and I work for a consultancy company in the Netherlands called Open Value. And this talk has nothing to do with what I do in my day-to-day job. And has everything to do with my son having too much Lego. If you have a son around 8 years old, he probably has collected a big basket of Lego. But he likes to build Lego sets, likes to build from the pictures and from the instructions. However, if you toss in all the Legos inside of a bin, then all the pieces get mixed together and, well, he needs to find all the little pieces. And he has an attention of an 8-year-old. So every other brick that will fit or looks nice is chosen. So it's up to me to figure out where all the bricks are and then give it to them and he can build it. So that's probably a job that I can do in a couple of weekends. So why not automate that and take a couple of months to do so? So my idea was to automate this process, create a automatic hopper and then a camera that scans the Lego bricks and then sorts them into different bins. So well, I needed to have some kind of image recognition or better even object recognition and machine learning. My day-to-day job is in Java. So why not use Java, right? So that was also my first hurdle because, well, if you're doing machine learning, the easy way is to do Python. You can take the right road, or you can take the left road, which is on fire and broken and, well, on the construction, you never know what's in there. But on the right side here, there's a snake on the road. So, of course, I took the left side and started out with Java. Well, the first thing you're probably going to introduce with machine learning are a lot of terminology, like loss function, gradient descent, Adam, hyperparameters, and all kind of that stuff. All that stuff confused me as hell at first, because I'm not a machine learning expert. I'm just a Java developer that likes to use Java, and I would like to use machine learning. I would not like to reinvent the wheel and reinvent new models. So with that, I will take you on to my journey, explain the most important terminology that I encountered during my journey, and let's see how that goes. Well, in Python, there are a lot of frameworks out there. There is PyTorch, TensorFlow, PySky, all kinds of things. But what are the frameworks in Java then? Well, I filled out all the frameworks that were no longer actively released. So I took only the frameworks that have a release in the last year and are free to use. So I got Deep Learning for J. That's actually the first framework that I started out with because that was the most popular one when I started. I came across Elky. But Elky is a more scientific-driven framework where you can test out models and that kind of stuff. And well, I was not into model building, so that one was gone for me. And then we got the Deep Java library, or DGL. And DGL has a wrapper function around existing machine learning frameworks, like TensorFlow, like PyTorch, and all that kind of stuff. So that also looks nice. And a year ago, I looked into that. So I did some benchmarks. I ran these benchmarks on a AWS machine with a GPU on it. And with the DGL, well, results are quite good. And with the Deep Learning for J, it was actually killed out once it started to learn with the model. Somehow there was a memory leak or something, and it was just killed when training on CPU-based. So that was annoying. Also, deep learning for Java, as you can see, takes a way longer time to train the dataset than deep learning for J, or DGL, sorry. They all have a D and a J in it, so that's really annoying names. So I switched to DGL then. But what about Python then? Because, well, everybody knows that Python is the de facto language to go to if you want to do machine learning. So what about that? Let's compare Python with Java. So the comparison in Java is based on the Deep Java library with PyTorch as an engine. That's because there is also a PyTorch engine in Python, hence the name. So that way I was comparing apples with apples, or at least I thought so. As you can see, Java is a little bit slower in learning and training the data. That's true for both on CPU and both on GPU. On GPU, the times are quite slow, quite fast, so it doesn't really matter that much. But if you have a large data set and large number of things to train, then this might add up. But how about using Java for predicting images? What if you have already built your model and we're just using Java for getting the prediction out? This is actually where Java exceeds Python. So somehow Java is faster in predicting one image than training in an entire data set of images. So if you want to use machine learning and want to get the prediction out fast, use Java. If you want to train a model, use Python. So why is Python that fast then? Well, because you're not training on Python. Python is just a wrapper, an API, onto an engine, and that engine is running in C++. So you're not actually using Python to do the machine learning for you. So actually, if you say I do machine learning in Python, you're actually calling a wrapper that's calling C++. And the same thing holds true for Java. The DGL library is just a wrapper API for the different frameworks. It has the same API for every framework, so that's nice. You can switch around engines if you would like. So you can use the same code for TensorFlow as for PyTorch. That's really nice. So with that out of the way, let's confuse some machine learning. I took this example as a easy example to grasp for us. Because if I wanted to dive into Lego immediately, that's a quite big leap. So starts out small with some confusing images. Well, what do you need to do if you want to verify this? I wanted to verify if this meme actually holds true. So first off, I need to divide this meme into different categories. So I get my muffins and some chinchillas out there and swap those around. And then we have a nice validation set. We have two categories, muffins and a chinchilla or dog. But if you want to train the machine learning model on only do those 8 images, well, that's not going to work because, well, A, the machine learning algorithm have already seen those images, so we don't want that. And 8 images are way too little information for the machine learning model to do any good training. You need around 1,000 images per category. So how are we going to do that? Well, my little devil is still on my shoulder, and I used Python to get some images from Google. I used simple image download and downloaded a couple of thousand images from Google. So that's nice. With Python, this is all the code you need. With Java, well, I don't want to go there. So running this resulted in a nice data set. This is just a random screenshot of my dataset, and as you can see, there is something wrong here. There are duplicate images in there. Because I used just the image search of Google, there are a lot of the same images online. Just different sizes, resized, just copy-pasted, and etc. So I needed to figure out how to get rid of all those duplicate images. Again, Python to the rescue with an image hash. An image hash is something like a checksum for a file. The only difference is that it's especially designed for images. So it does not care about the actual size of the image, the actual number of pixels, and creates a hash based on the actual content of that image. And it's also fun because it's a mathematical model. So if a similar image occurs, then it has a similar hash. And you can actually calculate the distance between those images, so you can compare how different images are. So that way I cleaned up all the most similar images. So images that are the resized ones or just a little bit rotated or zoomed in or whatever. And then I was left with 86 images from those 2,000 images that I downloaded from Google. So, continue. Let's go to Flickr. Flickr has a lot of images out there, and it has a nice API in Python as well. So we can actually use the Flickr API to download some images here as well. And with that, I had a nice little data set. And when I run the hashing algorithm again to filter out the duplicate images that were also in Flickr and also in Google, Then I left with 250 images per category. Still not enough for the machine learning algorithm. Well, I could venture on, download more images from Flickr or other images site or whatever. But there's an easier and faster way to do this. If you have a reasonable size data set, then you can use data argumenting. So what this does is it takes a image and it rotates it, flips it, zooms it, screws it a bit, and creates all kind of different images. For us, those images might look the same, but for the machine learning model, these are completely different images. It does not know that those are the same. And this actually works very well. And when I did this, I had around 1,700 images per category. That's nice. So I have a reasonable data set. You can do this again with Python quite easily. In Keras, there is a class image data generator that you can feed in some parameters and get this information out. So with the data set out of the way, and this was probably around 99% of the time that I used for this specific meme, it's time to actually build some Java code. Let's start out with a fresh and empty Maven project in IntelliJ, a clean POM, and that adds some dependency information to our POM. We can import a bill of materials in Maven and add a dependency for datasets because we want to iterate over datasets. We want a model zoo. A model zoo is, well, a bit weird name, but it's just the collection of different models. They call it a zoo because, well, maybe there are monkeys in there, I don't know. And I use the MXNet model zoo that will give me the MX engine for deep learning for J, or deep Java learning. I still mispronounce those. So let's do some actual learning. Let's create a Java class and let's create a function that loads a dataset. This dataset needs a folder, and then you need to resize it to a specific size, because the machine learning model only accepts a fixed number of pixels and doesn't really like random inputs. You need to resize it to a fixed size. So 224 by 224 for me. We need to transform it to a tensor because, well, the machine learning model works with tensors. And we have a batch size of 8. So let's zoom a little bit on batch sizing. If you train a machine learning model, if you train the complete data set, that's called an epoch. An epoch is divided into different iterations. Those iterations are based on a batch size. So if you give the machine learning model a batch size of 1, then it would train to recognize one image and then another and then another and then another. That's really slow. So the bigger the batch size, the faster it's going to be. But if you reduce the batch size, there's actually some research done in this. It will give the machine learning model a bit more noise because it does not see the full classifications that it needs to do. It just sees a little subset, and that way more noise in machine learning model means better results in the end. But my data set is only with 2 outputs, a dog or a muffin. So benchmarking is also the key here, and I did some benchmark with different batch sizes. I reduced all the batches that did not result in a 85% accuracy rate. And as you can see, not many batches survive. Only 8, 16, and 64 are left over. All the other batch sizes were faster or slower, but never give me a better result than 85%. So actually, I took a batch size of 8 because, well, it gave me the best results in this benchmark, and it sounds reasonable. And if you look at the actual speed, there is also a drop-off around 8. If you have a batch size of 8 to 16, it's not that much faster. And from 32 to 64, it's even, well, less performance gain. So, with that out of the way, we have a a learning class. And if we run this, we get a nice progress bar because we just loaded the dataset and nothing else. So we need to pick out our model. This is actually a screenshot of the Keras page, which has listed all kinds of models and how accurate the models were against a dataset of 1,000 images, all classified, and then see how the model did. And I wanted to run this on a lightweight machine. So I wanted to have a fast model and also a fast model to train because, well, I don't like to wait. So I picked ResNet 50 because it had all the characteristics that I would like. But you can look here and see what's best for you. As you can see, if the accuracy increased, then probably the training time or the inference time also increased. So it's a bit of trade-off if you would prefer faster or accuracy. So we need to get that model. So let's extend our class a little bit further. We need to create a model, we give it a name, and then we create a block. This is a ResNet block, so this is a class that comes from the model zoo. And here we can define what that ResNet model looks like. First off is the input shape. We see our 224 here again, so that matches with the resizing that we did before. And we see here the 3 in front of that, and that's the number of different channels. So we get red, green, and blue. That's just the normal input size. If you only got grayscale images, well, you can put in one there, for example. But this way, it can also use color information. Then we need to set our number of layers. Well, we need to build a ResNet 50 model, so those are 50 layers. And our output size is 2, because we want to classify dogs and muffins. So to use that model, we can just wrap it in a try, because it's auto-closable. And we want to train that model, so we can get a trainer. And we need to give it some trainer configuration. Well, first off is something new for me. That's a loss function. I will get to that in a bit. Then it will be more clear. And then we have to give it we can give it a accuracy evaluator, and that will actually show us the actual accuracy while we're training. So we don't only see progress, but we also see how good that progress is at that specific time. And we add some logging to see what's going on. So we have our trainer, and we set some metrics on that as well, because I want to have some metrics at the end. This way we can do that. And we need to initialize the trainer as well. Again, here comes the 3 and 224. And then we can say easytrain.fit and give it a trainer and the number of epochs, so number of times that it goes through the entire dataset. And we also have our validation set, and our validation set is actually the images that are split out from the meme. So the validation results are the actual results compared to the meme. So that's cool. And now my clicker is not working. Cool. So let's run this class. And through the magic of video editing, this is going a lot faster because I did this on my CPU. And CPUs are not really made for machine learning training, especially not my MacBook or this specific model because, well, kind of slow somehow. Anyhow, we can see here our accuracy and our loss function in the bottom. Our accuracy is a number between 0 and 1. If you multiply that by 100, you get the accuracy percentage. But this is the accuracy percentage of the training dataset. So you don't see the results yet. And we have our loss function. So what's the difference between accuracy and loss then? Well, accuracy is just how many images you guessed correctly according to your dataset. But the loss function is a little bit more than that. It's also accuracy, but it's also how convinced the model was predicting that model. Because it can guess correctly, for example, that it's a dog, but it's only 50% sure about that. If you train it a little bit more, it might have a 80% confidence. So that means the loss function goes down. So if you have a loss function of 0, you will be having a perfect model. a model that predicts your classes with 100% certainty and 100% accuracy. I have not gone that far. But this is something you keep in mind. So the loss function actually is a better metric of measuring how good your model is. So let's continue. And when it's done, it spits out that well, the validation is done and spits out some metrics. So now we have our model. Nice. But we want to use it later, so we need to save it as well. So we save it to a model path, give it a dir, and then here comes another mindfuck for me. That is, the labels are not saved inside of the model. So you have a model that can predict images, but does not know what the actual labels are. So you have to save the labels or the classifications in a separate file. And this is just done by spitting out those labels in a line-by-line based text file. And in the end, it will look something like this. A model file with a params file and a text file with the actual labels. Cool. And we're done. This is where most of the tutorials online end. You now have trained a machine learning model. Good luck. Okay, let's go a little bit further then. Because we actually want to use this model. We just didn't train it for nothing. So we can actually copy-paste a little bit of code of our training stuff, because we here also need to get a model, because the framework needs to load up the saved model, but it does not know what the model actually looks like. That information is not stored inside of the model. So you need to create an empty model and then load in the actual values that you saved before. This is easily done by calling model.load, and then you have your model again, and this time from your saved state. But then in our training, we had the dataset that had some translations, and this is also something we need to do for our usage, because we need to do the same transformations that we did whilst training when we were actually using it. So again, we need to resize it and spit it out to a tensor. And that's about it for the translator. Then we can actually come to the predicting part, and that's calling the new predictor on the model, give it an image, loading it from disk, and then calling predictor.predict, and then you get a classifications class out of it, and there you can get the top k of the top results from those predictions. So you get an array list of predictions, with the first entry having the most confidence and the most, well, what he thinks is the best. So if we run this, we get our muffin out of it, and we can see that it has a probability of 74%. Yeah, and it thinks that it's a dog around 25%. So this way, well, the model did good. This was the actual image, so yeah, looks like a muffin to me. So if we run this through all of the test set, we can create a confusion matrix. This is also something that's well, very many times done in machine learning. On the right side in red, we see what the actual label was, and on the top we see what the machine learning model actually thought about it. So in our muffin case, with only 8 images, it predicted that the muffin was correct 5 times, and it thought it was a dog 3 times. And those are the images that it thought it was a dog. With the dog part, it's actually a little bit better. Only 1 dog was misclassified as a as a muffin. So this is not where I would like to end. So let's make things better. Well, actually, if we train this model for a number of epochs, for example, 20 epochs, we can see that our validation accuracy peaks out around 4 epochs. So it would be dumb to train much further than, let's say, 5 or 6 epochs. because the model does not get any better. It only consumes time and resources, which is a shame. Unfortunately, this is not supported right out of the box. There is an issue from 2000 that requests a early stopping configuration. With an early stopping configuration, you can say, okay, stop training after X amount of epochs, or if the model hasn't improved in X amount of epochs, or if a specific target is reached. So luckily, this issue has some code attached to it, code that actually worked. So as a copy-paste developer I am in my spare time, I copy-pasted it, altered it a little bit, and put it into my class, and create a class for it, the early stopping fit class, and that way I can configure the early stopping configuration with this class, and it's quite easy. And I also added a callback, so when every epoch finishes, it calls the callback, and then I can check if the actual loss function is lower than the previous one, then it means it's a better model, and I can save it to disk. Because if I don't do that and let the early stopping just continue, it will probably do at least one more epoch. And that means that one more epoch is probably less good than the previous one. So I don't want the last result, I want the best result. And this way I can get at the result. So a little bit about learning rate. Because a epoch is done, you have to change a lot of numbers inside of your model to make it work. And when the machine learning model trains, it alters all kinds of numbers, and well, in the end, it gets better at the results. But it's a little bit like this game where you have a bar and you have to hit the space bar exactly at the right time to get the right results. The only problem is the machine learning model only sees the time when you hit spacebar. It sees how good it did at that specific time. It doesn't know if it's the best it will ever be, or is there any other place that's even better. And if you want to get to that specific point, you need to go through all the numbers and change them all. So you can imagine if you do this by, let's say, adding 1, and you need to go to 1,000,000, that can take a very long time. So what it actually does in the first iterations is go to add, for example, 1,000 or 10,000. So you're actually not with the nice resolution, but skipping ahead specific points. So this is not going to end up with at the correct result. So we need to slow down. If we could just start out with adding 1,000, we would overshoot our target, and then it would see that it overshot, and then subtract 1,000, and well, it undershot the target, so that it wouldn't get any better. So we need to slow down at some point. So there are optimizers for learning rates. So you start out with adding a lot of numbers, and then slowly ramp down and add only small numbers, so it can improve a little bit, but improve more towards the actual goal. So I did some tests with some optimizers that were out of the box. Some did really good in the beginning and then shut off into the distance and was killed by the early stopping fit because it did worse every time. But actually the Atom optimizer gave me the best results. And the Atom optimizer is also probably the most used when I looked into this. I don't know now because, well, probably outdated. But I used the Atom optimizer, and well, it actually did quite well. So how can we use that? We just need to add a single line to our training configuration and say that we need to have the optimizer Atom. And we can configure that optimizer as well, but let's just use it out of the box. And let's see how it does. And this time it did a lot better. It only misclassified 1. And I still don't know what it sees in that muffin that's dark, but I really can't convince it any further that that's not a muffin. So, with this out of the way, we can do something else. We can do transfer learning. the model, the top layer is the input layer, and then it goes through a number of layers. And what transfer learning actually does is it will lock out the first layers because you are using a model that's already trained. Let's say the model that was trained on 1,000 images. So it knows 1,000 images. Then you lock in the first layers, and the last layers you remove. So it does not know anymore what the labels are and how to connect the actual image to the specific layers. And that way we can introduce new layers and, well, use it for our advantage and try and see how that goes. If we want to do this, we have some kind of criteria API that we can use. Won't go through all the steps, but well, you can see that there's a filter for layers, for the model type, and how you want to use that specific model, and it gets it from the model zoo. And then we need to alter the model, and here comes the machine learning part, the part that I don't like yet. Because, well, I actually need to do some machine learning things here. I need to grab the block, lock the layers, remove blocks, add flattening layers, and all kind of that stuff. And that way I can tune the model even further. But, well, when I did this, I came only with 50% accuracy. So a toin cost would be better. So this was not the way for this specific use case. It could work for your use case, but it trains a lot faster. But in the end, the accuracy that you're going to get is less. So what about Python and Java together then? Because what we can do is use Python to create our model, because we have, for example, TensorFlow in Python and PyTorch in Python. And there are a lot of tutorials about how to create a model and how to fine-tune it, and all kind of fancy machine learning stuff is out there and ready to be used. We've also seen that Python is a lot faster in training, so your training is done earlier. So that's also good. So how would we do this then? We first can load up the model that's been saved in TensorFlow, for example, and save it as a saved model. A saved model is an open source standard for machine learning models, and this model is understood by both TensorFlow and the deep Java library. So this is something we can actually load. And we can actually use the doing class from before, but we need to add the TensorFlow engine to our POM, because we're actually going to use the TensorFlow engine in here. And we need to tell it to use that engine. We can also point it to an actual TensorFlow installation on your disk if you would like to do that, but well, we can do that. And here we have the criteria API again. This time we don't search in the internet model zoo, but search on our disk and load it that way. So if we do this, we also need to do the same transformation we did in the learning of the model. And this model was trained by 150 by 150. So it's different size, different model, but this way we can use it as well. And the prediction part is exactly the same as we used before. So that's nice. If we run this, we get a lot of red stuff, but well, that's just the TensorFlow library spitting out things. But the bottom line is that it spits out the classification just like we like. The DAISY class was the image that was inputted, and it classified it correctly. So this way you can use Java with a Python machine learning model. So let's transfer to Lego then, because we now know how to use a machine learning model, how to train it, and do all kinds of things. But for the Lego dataset, there is no Lego dataset out there that gives me for every, well, popular 100 or 1,000 bricks, thousands of images. So I need to figure out a way to do this. Well, I was looking online, and there were some people that actually did this before, and they all tried to generate the images and all failed. So naturally, I of course tried to generate images, because why not? I hadn't had any better solution at that point. So I want to generate images. So how can you do this? These are the actual generated images, so they don't look that shabby to me. They look like the actual thing if you look from afar. And the machine learning model does not see many pixels, so should work, right? So how can we do this? Well, first off, I needed to go to the Rebrickable database. It's a website online that has all information about all the kind of bricks, because I wanted to train against the popular 1,000 bricks. The only problem is all the Lego bricks are, if they have a sticker on them or if they have a print on them, they have a different number. And those things are used as well. But in the end, they are all based on a simple block, for example, just a block with a image on them. So I want to reduce that to a specific base block. So that's why I use the Rebrickable database to figure that information out. And then there is a LDraw CAD images library online, which has all kind of nice CAD drawings of all the Lego bricks. Only that format is a little bit proprietary. Luckily, there is a LD View image application. That's the application that you see in the center. It's a Windows application, unfortunately. But hey, it can spit out a POV file. And POV, we get to that in a little bit, can generate ray-traced images. So it can actually create very good and realistic looking images. So this is an example file of a POV file. It's just a text-based definition of your scene. You can instantiate lights, you can move lights around, you can set the background color, you can rotate your image and all kinds of things. You can all do that with some bash scripting, just finding and replacing stuff inside of the file. So then I come to a little dilemma, because do we need to zoom in or zoom out? I thought that if I would give the machine learning model the actual size of the Lego brick, it would do better, because then it also had information about the actual size. But unfortunately, that's not the case. The zoomed-in versions work better. With the zoomed-in versions, I got around 85% accuracy, and with the actual size, it's barely made it to 65% accuracy. So that's something to keep in mind. Probably because, well, like I said, the image is resized to 224. Then the actual size of the model is probably a few pixels across. That is not enough information for the machine learning model to make out the specific brick. So zoomed in models it is. And then we need to change our application again. We can use the same application as we used before for our dog versus muffins, and just change the output size to, for example, 100. And I took 100 here, another 1,000, because 100 images to generate takes a very long time, a few nights on my MacBook. And then training on it takes around 9 hours. So that's also something that, if you scale that up to 1,000, then that's 90 hours. So that's a hefty price. So I did some training with only 10 images instead of 100, because, well, I can do more iterations and more epochs in that way. And actually, the best result came around 17 epochs. And the best result for 100 images were around 15 epochs. So training much further than 20 epochs is probably not advised. But on my simulated images, like you can see, I managed to get around 86% accuracy, 87% accuracy. That's quite nice. Because there were also some images that were really hard to distinguish myself. So, well, I was chuffed with 80%. So if I would input the real images, so the actual photographs that I took from some Lego bricks, it stuck around 35%. Well, I only had 3 images that I actually took pictures of, because I was in a rush. But I plotted this into a confusion matrix again, and then I saw something funny. It all thought it was a 3001 brick. It just spit out the first brick, and, well, not really with a high accuracy or high probability. So it just was guessing, and just the first thing that comes up in his mind is a 3001 brick. Then, so this way you can get a nice 35% accuracy. Great. So looking a bit further in all the epochs, at around epoch 47, when the actual accuracy of the simulated image went down, the accuracy of the actual images went up. It was trying to figure out, it was trying to put them into a better category. The only problem is I still have not seen any prediction of the 3004 model. So what's going on there? So if we look at our actual images, you can probably tell which one are generated and which one are the actual photographs, right? And this is also a problem for the machine learning model. These images are completely different. I could as well toss in trees, houses, whatever. It would still have guessed a 3001 image because that's just what it knows. It does not know anything about the other stuff. So the important part here is that, well, those images don't match. So failure is always an option, although hopefully temporary. So what's next? I want to use actual images, but if I want to use actual images, I need to create the actual device to create the actual photographs and the actual conveyor belt that the bricks are on, so the background is the same and all the lighting is the same. And then I can still use the generated images as additional input for the machine learning model. As the machine also can generate a few hundred images, but I input manually, place the brick around a bit, take a few images of that. A, it's going to take a very long time, and B, probably not all different rotations are given. And when I generate a little bit more images for the machine learning model, it then can combine that information and probably end up with a better result. And I need to scale up the resolution of the generated images because, as you saw, there were some jagged edges on the actual brick. Well, real-life bricks don't have jagged edges. So with that, I need to do my homework again and go back to the drawing board and build some actual sorting device. So maybe that will be my next talk. For now, are there any questions? The repositories are on my GitHub. There are 3 repositories for this talk. The Java doc versus muffin, the machine learning benchmarks, where all the benchmarks are, and the Lego sorter, well, that's about to be filled. Are there any questions?
So how long did it actually take from start to end?
I started about 2 years ago. But I'm a dad of 4, so the kids take a lot of time. And this is only done in the evenings when I have time off and have the energy to do this. And it's been an on-off project. Well, some months at the end and sometimes a half year and nothing. And then switching between frameworks also did not give me any confidence boost or morale boost. So I need to get into this. Are there any other questions? All the way in the back. Microphone is coming your way.
Hi, I wanted to ask about if you're switching between Python and Java for training and predicting, if you had an opinion on your data pre-processing for your training versus something in production.
I heard only the last part, but let me summarize. If I have an opinion on data in testing and actual production?
Yeah, so if you use Python for your training, and so you do your data pre-processing in Python, but then you want to use Java for your in-production predictions.
Okay. So if you use your training in Python, well, there are just images going in, and if you do the same transformations, then the same results should end up. And I actually verified this with at least PyTorch. The same probability, the same classifications came up for at least the things that I checked out. That was the flower model, but well, the same image processing is being done on both the Python as the Java side. And if you do that, then you're in luck, and then it can work out really well. Any other questions? I know it's early, but if there are no further questions, then I would suggest you all get a cup of coffee and see you on the next.